Today I am going to undo the process I did in the last class. What I did in the last class, I just broke an egg. But I am vegetarian, so I am going to undo the process. Not like I am just kidding. Actually, I am going to undo the process because I want to tell you about solid spheres. Means I want to just fill the hollow space inside the sphere with some substance, having some mass, having some density. In the last class, we were talking about spherical shells, which had its mass distributed on its surface. Surface means we are talking about surface mass density. But today we are going to talk about volume mass density, because the mass will be distributed in a volume like that of a sphere. So we are going to calculate potential and field due to a solid sphere inside, outside, and on the surface. So for that we need to understand what is solid sphere and what is spherical shell. So spherical shell is something like the plastic ball with which we play in our childhood, inside hollow, just like that of football also. It is hollow from inside, and thickness is that much small that it is negligible. So we consider the mass to be distributed on the surface. But solid sphere is something like that of cricket ball, or like tomato, or like some apple, you can say that, which has its mass distributed throughout its volume. Means its volume is filled with some mass, and it has volume mass density. So there are several methods from which you can calculate potential field due to spherical shell, ring, disk, etc. But we'll talk about some easy methods. So let's start. In the last class we were talking about spherical shell and derived the expression for potential due to spherical shell, right? So you have seen that Jawbreaker, a candy. If you have seen, I will recommend you to search for that, or I will paste a picture of that in this video. So Jawbreaker looks something like, it has a small spherical candy of suppose white color. It has a small coating of blue color, then another of yellow, and more. Means it feels something like a small spherical shell is coated with greater than infinite spherical shells. Means I want to tell you that suppose there is a small spherical shell of very small radius. Suppose tell it tends to 0, then it will look something like a point. And if I give it a coat of another mass, then it will increase its radius. I will add another coating, another, and each of the coating will also have a spherical shape. Means it will look something like a spherical shell. Means a sphere, a solid sphere is actually combination of infinite number of spherical shells. I hope you are able to understand. I'll recommend you to see that Jawbreaker, so that it will be easier for you to understand what is actually relation between spherical shells and solid sphere. So consider this as a solid sphere. Suppose there is a spherical shell at some distance x from the center of this sphere, and obviously this will have some thickness which is negligible, and let us call this dx. So actually this solid sphere is made up of small infinite number of small infinite number of spherical shells starting from this point to ending at this point, right? So for this, if I consider this elemental spherical shell, this will start from radius of 0 until radius of r. Suppose this sphere has the radius of r, right? So if I consider a point to be at this point P outside the spherical outside the solid sphere at a distance of small r, suppose, then we have to calculate the potential due to this spherical shell. And if I calculate potential to this elemental spherical shell, I can integrate it for a radius of nearly 0 to that of capital R, and after integrating this we will get the total potential due to this solid sphere at this point P. So what was the expression of potential due to spherical shell? In the last class we derived that the potential due to spherical shell is minus g m by small r, means the distance of the point from the center of the spherical shell. So here for each of the spherical shell starting from x tending to 0 to that of capital R will be r, because each of the spherical shell will have its center at O, and O is at a distance of small r from that of P, right? So suppose this spherical shell has mass m1, and if we consider infinite number of spherical shells, suppose we have divided it into n number of spherical shells, then for the first spherical shell it will have the potential minus g m1 by r. For second one it will be minus g m2 by r till minus g mn, means the last from the first sphere to the last spherical shell, the total potential due to this solid sphere will look something like this, which will be equal to, if I take common, minus g by r, we will get m1 plus m2 plus dot 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 mn. And we know that if I add all the masses of all the spherical shell, it will be equal to mass of the solid sphere, right? So this will be equals to capital M, means mass of the solid sphere. So this will be equals to minus g m by r. And if the point is on the surface of the sphere, it will be the small r will be equal to capital R, and for a point on the surface the potential will be equals to minus g m by capital R, right? Actually this method was quite simple because I have just used some plus signs and added the potentials, but it will be more complex if I will use rho, means volume mass density, and try to find out dm, means elemental mass of the elemental spherical shell, and do integrations to find out the total potential due to the solid sphere. But it will make you more comfortable with the mathematics, so I will give it to you as a homework, and obviously this is present in my notes. If you need any help in case you are unable to find, then you can use my notes. So actually now comes the challenge. Now I am going to find potential inside the solid sphere. Inside the spherical shell it was minus g m by capital R, a constant value, and same as that of potential on the surface of the spherical shell. So suppose this is a solid sphere. I am here at a distance of small r from the center, that is O, and I want to calculate potential at this point P. Actually here you can see that there is some mass present here, means inside this surface, and some mass outside the Gaussian surface containing P, right? Here you can say that obviously this spherical shell will give it some potential, because we know that minus gm by r is the potential inside a spherical shell, and if I consider all of this spherical shell, it will have some total potential due to the spherical shell. And here there is a solid sphere, and this solid sphere and the point P lies on the surface of the solid sphere, means it will have some potential due to this sphere, this solid sphere. So here I am going to use rho. You know rho is the volume mass density, means mass per volume. So what is the mass? Let us suppose the mass of the sphere is m, volume of the sphere will be, we know that the radius is equals to capital R. In the last picture, I guess, yes, in the last diagram I show you that the radius of the sphere was capital R. So here I am also taking capital R as the radius of the solid sphere. So volume will be equal to 4 by 3 pi r cube. And now we first calculate potential. Net potential will be equals to potential due to this solid sphere, that will be equals to V1, plus potential due to spherical shell, means V2, outside the Gaussian surface containing point P. So what will be V1? So we know that for a point on the surface, potential due to a solid sphere will be equals to minus G, suppose this is mass m1, minus G m1 by r. Here r is smaller. So we want to calculate m1. Here m means surface mass density into volume. Mass into volume into surface mass, volume mass density. Volume into volume mass density will give us mass. So for mass we can replace it with minus G. Here the volume will be 4 by 3 pi small r cube rho by small r. Here we can cancel a small r, 4 by 3 pi r. And rho, I can write rho as m by 4 by 3 pi r cube. Here 4 by 3 pi, 4 by 3 pi will cancel out, and we are left with minus G r square m by capital R cube, right? So now we want to calculate V2, potential due to spherical shell. So potential due to spherical shell for a point inside the sphere will be equals to minus G m by r, radius of the spherical shell. Suppose here I have taken a spherical shell at a distance x from the center. This is an elemental spherical shell. With some mass. So I can put minus G. This spherical shell will have potential, not let us denote this with V naught. Supposing this is V naught, means potential due to this elemental spherical shell at point P. So here G, mass of the spherical shell will be 4 pi r square, the surface of the 4 pi x square. Here the radius is x, 4 pi x square dx is the volume of the spherical shell. because suppose this is a spherical shell. Here the surface is 4 pi r square. We know the formula. Suppose the spherical shell is like a football. I cut the football and just open it. Like if you have seen nowadays people are opening the globe and showing that actually the world map is wrong, something like that. I am not from a geography background, so I am telling you about physics. So if suppose I have cut the spherical shell, football, and open it, then it will have some thickness dx and surface 4 pi r square. Here x square because the elemental spherical shell has the radius of x. So 4 pi x square into dx will give its volume, like something like sheet. This sheet has dx thickness and area of 4 pi x square. So here is the volume of the spherical shell, and volume multiplied with this rho. Rho means m by 4 by 3 pi r cube by x will give us potential due to this elemental spherical shell. But we want to calculate potential due to all of this spherical shell. So we will just integrate it. If I integrate v naught from 0 to v, and this here for the point spherical shells lying outside outside this point, means outside this spherical solid sphere, all of this spherical shell is lying outside the point P, means point P is inside all of this spherical shell. So for point P to be inside the spherical shell, the radius is actually from this point to this point. So what is this point, means what is the value of radius at this point? It will be nearly smaller, a little bit greater than smaller, but we can consider it to be smaller, to capital R. So now I have to integrate this thing. Here x will cancel out, 4 pi will cancel out. Now I have actually let me erase these calculations so that I can solve this problem. So from last equation, now I present with this equation where v2 is integration of small r to capital R with a negative sign, 3g mx dx by capital R cube. So here this thing is constant, so I can take it out of the integration, and integration of x square will be x square, x will be x square by 2. So integrating x square by 2 from small r to capital R, we will get 3g m by r cube. I am taking the negative sign inside the integration, then the limits will change and it will be equals to, if I take x square from x square by 2, if I take 1 by 2 common, it will look something like this, and this will be equal to small r square minus capital R square, because if I integrate generally it will have a negative sign, and capital R square minus small r square, but if I take the negative sign inside, it will be small r square minus capital R square. So now this is v2, so I have to add v1 and v2 to calculate net potential. So net potential will be equals to, if I take minus g m by r common from both of the terms, it will look something like minus g m by r cube whole into 3 by 2 small r square minus 3 by 2 capital R square plus r square, right? Sorry, if I take minus g m by r cube from this term, then obviously the negative sign will change, means this term will have the negative sign, this will be positive. So r square minus 3 by 2 r square will be equals to gm by r cube will be equals to 3 by 2 capital R square minus 1 by 2 small r square, right? So if I take 1 by 2 common, it will look something like gm by r cube, 2 common, 3 capital R square minus small r square. This is the potential due to a point inside the solid sphere. So now here we are present with potential due to a solid sphere at a point inside the sphere, at a point outside the sphere, and on the surface. So from this we can calculate the field, and we can see one thing, that if I replace r with 0, because for a point means at the center, the radius of the sphere means radius of the Gaussian surface will be 0, and there is no mass inside. So here smaller will you can see it from this thing. Here for this point small r will be 0, and hence this will be equal to minus gm by 2 r cube multiplied with 3 r square, which will be equal to minus gm by r multiplied with 3 by 2. Minus gmr is potential on the surface, means for a center, at center the potential due to a solid sphere is 3 by 2 times of that on the surface. And here outside the surface, minus gmr is potential due to solid sphere, looks like something for a point mass, right? So if I differentiate it with respect to dr, means take negative gradient of this thing, I will get the field. You know, negative gradient of potential energy is force, negative gradient is potential is field. So taking negative gradient of this thing, I will get minus gm r minus 1, and if I take the differentiation, I will get a negative sign in front of it, something like minus gm by r square, and negative gradient will give you a negative sign. This is the excuse me, this is the field due to solid sphere at a point outside the sphere. And if I replace small r with capital R, potential will be this much for a point on the surface. And if I multiply this thing with 3r square, the thing will be constant for dr, and multiplying this thing with small r square, thing will look something like g m r square by 2r cube. Differentiating it and taking negative gradient of it, I will get 2 smaller, means 2 will cancel out, and it will look something like gmr by r cube. Here you can see there the field is increasing with increasing distance for inside the sphere, means the field will increase with increasing distance from center till it reaches the limit of capital R, means it has the highest negative value till this point on the surface. You can also see that if I increase the means take the point at distance, if I increase the distance of the point from the center, the Gaussian surface will be larger, and if this surface is larger, it will contain more amount of mass, and if the mass is increasing, the field will increase and force will increase. You can calculate potential energy by multiplying mass with this, and if you are able to get potential energy, you can also get force, because force is negative gradient of potential energy. Multiplying potential with mass, you will get potential energy, and taking negative gradient of potential energy, you will get force. You can do it yourself. This is homework for you. In the next class, we will talk obviously about that of electrodynamics, and we'll compare this with a spherical shell are being charged, distributed inside it. So this is for today. Thank you.